Have you ever been stopped at a red light and just looked up at it? It's just hanging there, totally still, held up by a couple of wires. And it seems so simple, right? But it's actually this really cool physics puzzle hiding in plain sight. Today, we're going to pull back the curtain on those invisible forces and figure out just how much work those cables are really doing. Let's crack this case together.
So yeah, that's the big question, isn't it? It's not just about holding up the weight, it's this constant, perfectly balanced tug of war. We're going to treat this whole thing like a mystery we need to solve, and physics is going to be our detective toolkit. All right, first things first. Every good detective needs to know the facts of the case. So let's lay out everything we know about our suspended traffic light. Okay, here is our case file. We know the traffic light has a mass of 30 kilograms. The cable over on the left is pulling at a 35-degree angle, and the one on the right is a little steeper at 55 degrees. But the most important clue of all, the light is at rest. In physics, we call that being in equilibrium. This means it's perfectly still, not moving, not accelerating, nothing. That right there, that's the key that's going to unlock this whole mystery for us. These are all the clues we need. So now that we've got our facts straight, the next step is to, visualize the scene of the crime, so to speak. To really get what's going on, we need to map out all of those invisible forces pulling on the light. And for that, we're going to use one of the most powerful tools in any physicist's toolkit. We're going to create something called a free body diagram. Now, that sounds way more complicated than it is, I promise. First, we just simplify the entire traffic light down to a single dot. See? Easy. Second, we draw an arrow pointing straight down. That's gravity. It's weight. Then we add two more arrows pulling up and away from the dot. Those represent the tension in each cable, which we'll just call T1 and T2. And just like that, we've made all the invisible forces visible. And that's the whole point of a free body diagram. It lets us ignore all the distracting stuff, like the shape of the light or the color of the poles, and focus only on the forces. It's the blueprint we're going to use to solve our puzzle. Okay, so we can see the forces now, but what are the rules they have to follow to keep that light hanging perfectly still? This brings us to the core concept that makes this whole thing work, the idea of balance. It's called static equilibrium. It's kind of a fancy term for a really, really simple idea. If something isn't moving, it's because all the pushes and pulls acting on it are canceling each other out. The net force, the total force, is zero. In that tug of war, nobody is winning. Now here's what's really cool. We can break this idea of balance down into two simple directions. For our light to be in equilibrium, two things have to be true. First, any force pulling it to the left has to be exactly matched by a force pulling it to the right. And second, all the forces pulling it up have to perfectly counteract gravity pulling it down. Left equals right and up equals down. That's it. Now, to use those rules, we have to break our angled forces into their horizontal and vertical parts using a little bit of trigonometry. Don't worry, the math here is just a tool to help us see everything clearly. This table shows us that T1, the left cable, has a part that pulls left and a part that pulls up. T2, the right cable, has a part that pulls right and a part that pulls up. And gravity? Well, gravity's simple. It only pulls straight down. We also calculated the light's weight, 30 kilograms times the acceleration of gravity. That gives us 294 newtons. A newton is just the unit of force we use in physics. All right, the detective work is done. We've got our clues, we've got our blueprint of the forces, and we know the rules of balance. It is time to put it all together and finally solve for the tension in each of those cables. Let's do this. Let's start with that horizontal balance. Now, this equation might look a little intimidating, but all it's really saying is that the rightward pull from cable 2 has to exactly equal the leftward pull from cable 1. They're in a perfect standoff. And now, for the clever part. With a little bit of algebra, we can rearrange that first equation to find this really important relationship between our two unknowns. We don't have a number for T1 or T2 yet, but we now know exactly how they're connected to each other. This is our big breakthrough. Next up, we apply our second rule, the vertical balance. This equation just shows that the upward pull from cable 1 plus the upward pull from cable 2 have to team up to perfectly fight against the downward pull of the light's 294 Newton weight. And here it is, the aha moment. We can take that relationship we found from the horizontal equation and plug it right into our vertical one. This move replaces T1, which leaves us with just one unknown variable left to solve for, T2. We've totally cornered our suspect. After we run the numbers, we get our first answer. The tension in that right side cable, T2, is 241 newtons. That's the force it has to exert, constantly, day in and day out. An engineer would need this exact number to pick a cable that's strong enough for the job. And once we know T2, finding T1 is a piece of cake. We just plug that value back into that key relationship we found earlier, and boom, the tension in the left side cable is 168 newtons. Case closed. And notice it's less than T2. That's because its steeper angle actually makes it a bit better at holding the light up against gravity. So, we've solved this specific puzzle, but what we've really just done is demonstrated one of the most fundamental laws of the entire universe, a law written by none other than Sir Isaac Newton himself. This is Newton's first law of motion. You might have heard it called the law of inertia. It is the ultimate rule for anything in equilibrium. From a traffic light hanging over a street to a skyscraper standing tall against the wind, if it's not moving, it's because all the forces acting on it are in perfect balance. Let's just tie it all back together. Our traffic light is the object at rest. The net force is just the sum of those three forces we found. By doing the math, we proved that the sum in the horizontal direction and the vertical direction is 0. And because of Newton's first law, the light has no choice. It must stay at rest. That law is absolutely unbreakable. So the next time you're stopped at an intersection, take a look at that traffic light, because now you know about the invisible tug-of-war that's holding it perfectly in place. And that kind of leads to a final thought. What else around you right now is being held in a state of perfect invisible balance? A picture on your wall? A bridge you drive over? Once you start looking for it, you'll start to see Newton's law in action absolutely everywhere.